So what we are doing, we are examining the second order circuits. We said how we can calculate, how we are going to find out the state equation, which is the mathematical model of a second order circuit. Example circuit was this parallel RLC circuit. We found the parametric state equations. And then we said the next step is to find a mathematical solution. Mathematical solution has got homogeneous solution. Let me go in detail. Homogeneous solution and particular solution. Summation of those two gives you the general solution. So we have done this in a parametrical, as a parametrical solution. So the numerical values are not included here. So from now on, we are going to move the numerical values. Depending on the numerical values, there are going to be some variations. So what is the next thing that we do is the second step. Find the parameters. So there are some cases that we've got to consider. Real roots. And then now, what do we mean by saying real roots? So we've got to go to the original example now. So this is our second order circuit. This is the state equation for this circuit. This is a parametric state equation. So we've got the element parameter values here. Independent source is a DC source, 1 amp independent current source. Resistors 200 ohm. Inductance is 50 millihenry. And the capacitance is 0.2 microfarad. And the initial condition of the capacitor is 12 volts. And the initial condition of the inductor is 30 milliamp. So if we put these values, these values in this A matrix, you're going to get this new numerical A matrix. In here, 1 over C times I. C is 1 over 0.2, 10 to the power minus 6, and inverse of it multiplied with 1 gives you that 5 times 10 to the power 6. So if you put the numerical values, our numerical state equation becomes this. Now we would like to solve this. The mathematical solution, parametric solution, we have done it already. In here we are going to do the numerical solution. So in order to find a solution, we've got to find a homogeneous solution first. Homogeneous solution first, and then particular solution, sum them up, find the general solution. So how are we going to find a homogeneous solution? In order to find this homogeneous solution, we've got to calculate characteristic roots. So we know the characteristic root is determinant of this equal to 0, isn't it? So what is SI? SI is, I is unit matrix. We have already done this. So SI becomes this. And minus the A matrix. A matrix is this. So minus 25, 10 to the power 3, minus 5, 10 to the power 6, 20, 0. So this is A matrix, this is SI. When you do the subtraction, so it becomes S plus 25, 10 to the power 3. So this minus make it plus 10 to the power 6. So this 0 minus 20, and S minus 0 gives you S. So determinant of this equal to 0. Then S squared 25 10 to the power 3s, multiplication of those two, minus this, there is minus here, so it's going to be plus 10 to the power 9, isn't it? So 20 times 5, 100, 10 to the power 8, sorry, equal to 0. So from this one, I am not going to do it. This is second order equation. You're going to find the roots of this. These roots are the characteristic roots. These values becomes minus 5,000 and minus 2,000. You do the calculation. So conclusion is this. Now roots are real roots. Real roots. When the roots are complex or when the roots are multiple roots, the solution, the general solution, the graph of your solution is going to change a bit. That's why we are examining the three cases depending on these roots. So we have found these parameters. So we can write the homogeneous solution right here. It's going to be VC IL homogeneous is equal to K11 K21 e to the power minus 5000 t plus, this is we have already done, 1 2 and K22 times e to the power minus 2000 t. In general, we have done it in the parametric form. We have found this homogeneous solution. So this is the calculated characteristic roots. The K values are going to be calculated according to the initial conditions. We are going to do it later on. So we know that row. So the next thing to do is to find the particular solution. So that was the homogeneous solution. So for the particular solution, let me use another color. So remember, now we are looking for now VC particular and IL particular. That's L, inductor current, that is. That's capacitor voltage, state equation, state variables these are. So question for that, question for that. So we, as we said already, if you remember the definition relation of these elements, that is IC is equal to C times dVC over dt, and VL is L times dIL over dt. Since the particular solution is in the form of the source is DC, source DC, then all the elements particular solutions are going to be DC. That means this voltage is constant, this current is constant. When you get the derivative of it, this becomes IC open circuit. Why is that? Because derivative of a constant is 0, so IC is 0, IC equal to 0, open circuit. And similarly, since IL is a constant, derivative is 0, then VL is equal to 0, short circuit. As we explained it already, we could use the circuit itself in order to calculate the particular solution for a DC source. So since IC is open circuit, so it's going to be, so you're going to remove this, and IL is short circuit, so that is not IL, the L element is short circuit, so there's going to be a current, that's this current, that's short circuit current, and the voltage of the this inductor voltage is also the resistor voltage. Definition relation is V times Ri. If the voltage is 0, then current is 0. If both of them 0, we already explained that, this is going to be open circuit as well. So conclusion is this. So this open circuit, so this current comes and passes through this inductor. So Kirchhoff current law equation, that is. So conclusion, IL particular solution is equal I independent current source current, which is equal 1 amp. So this is equal 1 amp. What about capacitor voltage? Since this is short circuit, this is connected to the capacitor in parallel, so the capacitor voltage is equal to 0. So that's equal to 0. So that is the particular solution that we found here. So I can write now, maybe write it in black color. VCIL general is equal K11, K21, e to the power minus 5000 t plus K12, K22, e to the power minus 2000 t, 20,000 t. So this homogeneous part of it, plus the particular solution for VC particular solution is 0, for the IL is 1. So that is homogeneous. That is particular. So what is left is the calculation of K parameters. How we are going to calculate the parameters? We said we are going to use the initial conditions, these two. But I've got 4 parameters, I need 2 more. How I am going to find it? I am going to find it directly from my differential equation. In here, if you replace t with 0, so let me do it in red, maybe it will be better. When t is equal to 0, so this becomes derivatives t equals 0 values, and when you replace this with t equal to 0, so this is going to be the VC0, that means initial condition, that's going to be only 12 volt, and that IL is going to be initial condition of the inductor is 30 milli. From this you can see that right hand side are the numerical values. So at the end calculation I can find the derivatives initial conditions. Let me write these derivatives initial conditions here. dVc dt 0, dIL 0 dt. So I can show you, so this is by hand you're going to do a calculation, it is a simple calculation, so we can directly take these results from, here. It has been calculated here, voltage derivative initial condition 4550 and 240. So escape, come to this. So this is 4550 and the 240. So I found this. So I have got all I need now. As I said before, 4 equations, 4 unknowns, but in practice it's going to be just only 2 equations, 2 unknowns. How it is going to be? Consider now that we see here. So this is our general solution. For the VC's general solution is K11 e to the power minus 5000 t and k12 e to the power minus 20,000 t, and that's 0. Okay. So if you replace now t equal to 0, 2 equal to 0 here, so left hand side is going to be the initial condition for the capacitor, which is 12 volts. 12 volts equal t equal to 0, that means e to the power 0 makes it 1, so k11, and similarly this is equal to 1, k12. So I found you two unknowns, one equation, and then I am going to take the derivative of this function now. What I get, dvc over dt is k11 times minus 5,000 e to the power minus 5,000 t. So what I have done here is the derivative of this, and then plus k12 minus 20,000 e to the power minus 20,000 t. Now if I replace t equal to 0 in here, so this is going to be, this becomes what? Initial condition of the derivative is 4,550. 4,550 times equal k, let me correct this one, minus 5,000 k11 minus 20,000. So t equals 0, this becomes 1, this becomes 1, so k12. So this is the second equation. That's why I said that is the first one. That's the second one. Two equations, two unknowns. You can calculate k11 and k12 here. So I remember that one is k11 is 958 over 3, k12 is minus 922 over 3. So what we have done here for the capacitor, you're going to repeat it for IL. I'm not going to do it, you'll do it. And then what you're going to observe is this. So this is what I have done and found this k11 and k12. For the inductor, if you do the calculations, you end up with the k21 is equal to this one, k22 is equal to this one. If you replace these k values in your general solution, that is the general solution. So let's examine the general solution graphs. So this is the inductor general solution, this is the capacitor general solution. So this general solution has got two parts. One of them the homogeneous part, the other one is the particular solution. But you can check your graph is going to start from the initial condition of your inductor, which is 30 milliamp, and your capacitor voltage is going to start from the initial conditions, which is 12 volts. So it starts from 12 volts and it goes. In here, for the inductor, I have got a particular solution, but in the capacitor, I do not have the particular solution. Means particular solution is equal to 0. We've already found that. So if you examine this, since the characteristic roots are real numbers and negatives, then these exponential functions, decreasing functions, disappear after a while. So this is going to means that is disappearing. What is left is going to be this particular solution. So in a short time, since these are exponentially decreased functions, these are going to disappear in a short time. So we're going to observe the particular solution. That's why we consider the homogeneous solution part as transient solution, because it disappears, and we consider the particular solution as a steady solution because we are going to observe this forever. So when you come to capacitor, initial condition, capacitor transient solution is this, and there is no any steady solution. It is quite interesting that after 10 microseconds, we reach the capacitor voltage reaches the highest voltage, which is 150 volts. That could be critical. Maybe that might burn some of the elements within your circuit. We don't know that. That's why the transient solutions, although they disappear, but it might be needed for the real analysis, because if it is 150 volts, it's critical for some of the elements within your circuit. So that means you're going to say that I am in trouble. So you've got to choose your element parameters according to this voltage limit. So what I am informing or insisting to inform you is transient solution might be critical in some cases. You might need to calculate it, although in some cases it is not that critical. So that is end of this video then. Let me stop it.